Hello students, welcome back. Let us resume our discussion in section 2. Previously we went through RSA encryption. RSA encryption is a public key crypto system, and it comes from a couple of large primes P and Q, and then create n by multiplying those two and finding another positive integer that is relatively prime to P minus 1 times Q minus 1. Put those two numbers together, we get an encryption key, and that is publicly released. By the way, P minus 1 times Q minus 1 is none other than phi of n, and then this condition, E and P minus 1 times Q minus 1 are relatively prime. That means phi of n and E are relatively prime. Also remember that RSA encryption system is a block cipher scheme, and if you have an original text, say capital M, then we can decompose that into equally sized blocks, M1, M2, M3, Mk, like that. And the last one will include possibly some dummy characters so that we get the same number of elements in this block. And then to each block we apply this encryption function, m to the e power mod n. This is the focal point, and we have to invert this. How do we do that? Well, if we apply something so that we get 1, that's what we want. So that's how the decryption works. So what we want is the inverse of this, and for that let's find the multiplicative inverse of E modulo P minus 1 times Q minus 1. Can we do that? Yes, we can, because these two are relatively prime. By the way, how does P minus 1 times Q minus 1 come into play? It is phi of n, remember that? So here we go. Let D be the multiplicative inverse of E modulo P minus 1 times Q minus 1, but if you don't like P minus 1 times Q minus 1, you can rewrite it as phi of n. Yeah, on second thought this looks better. Phi of n. And the description runs like this. D times E is 1 modulo phi of n. And then we can use the theory of the Diophantine equation. D times E is congruent to 1, can be rewritten as D times E is 1 plus an integer times phi of n. Yeah, instead of P minus 1 Q minus 1, let's use phi of n. And then we can run the decryption like this. C to the D power, that's going to be your decryption function. You see, C is ciphered number, ciphered digit string, and then apply the inverse map so that we can get M, and we are doing C to the D power, and by this C is M to the E power, so M to the E power to the D power. Maybe it's going to be better if I increase the font. So C is M to the E power, that's the encryption, so decryption goes like this. C to the D power, which is M to the E power to the D power. In other words, M to the E times D power. Okay, just the exponential. And E times D is 1 plus, 1 plus K times phi of n. So this is K times phi of n. So m to the 1 power, I can take it out. And then this is multiplication. So we can rewrite it as, okay, here we go. Phi of n to the k power. Now, what is m to the phi of n power? That is 1 modulo n, thanks to Euler-Fermat theorem. So we don't need lengthy explanation. We already talked about the multiplicative property of phi. So p minus 1 times q minus 1 is in fact phi of n. So it works out. It's Euler-Fermat theorem. This one is just 1. So 1 to the k power, we have just 1. What do you get in the end? Just m. So that's how the decryption works. Encryption, m to the e power. Decryption, c to the d power, where d is a multiplicative inverse of e modulo phi of n. Let's do an example problem. What did you do previously in the encryption example? P is 43, Q is 59, and multiply those, and the product is 2537. The public key is 2537, 13, and 13 is a prime number, so 13 is certainly relatively prime to phi of p times q, or phi of n, but you can actually check it manually, not that it is necessary. And then what did it do? We used this encryption to stop. So 18, 19, 14, 15, all right, that's STOP. And then we decided upon the length of the block. The key point is 25 because that's the last alphabet. 25, and then 25, 25, and then 25, 25, 25, and then 25, 25, 25, 25, kind of like that. But this one here, in between 25, 25, 4-digit, and 25, 25, 25, 6-digit. So we use 4-digit. Don't ask me why. And then we get the block. Okay, 4-digit block, 18, 19, and then another 4-digit block, 14, 15. So S and T in one block, and O and P in another block. And then apply the encryption function, m to the e power, and then mod n, and then we ended up with this. So right, we got this, we got this computation. So 2081 and 2182 from 1819 to the 13th power modulo n, and 1415 to the 13th power mod n. We did all those to get this. Okay, all right. Now let's start from here. Let's decrypt this. So from the same idea, 25, 25, and 25, 25, 25, yeah. So we have the block length of 4. So here, 2081, that's one block. 2182, that's another block. And then we're going to use the decryption, that is c to the d power. Let's see, what is the decryption key? So phi of n, which is p minus 1 times q minus 1, is 2436. So what we want is E inverse, in other words 13 inverse, modulo 2436. And finding this is gonna be major pain in the rear end, I have to say. If you have to do it with traditional paper and pencil method, you'll have to use Euclidean algorithm and then find this Bezout's linear combination expression. and then get all the way down to the linear combination of the GCD to find out. In the end, if you do it right, you're going to get 937. That detail is left to you. We went through all those in lesson 2 and lesson 3, so I'll leave you there. If you do it right, 937. So that's the decryption key. And then once you have encryption key and the decryption key, P and Q will be discarded, and we no longer use it, so that nobody will be able to track it down and break the entire system. We just use the decryption key, and let's just decipher the outcome. So C to the D power applied as to 2081. So 2081 to the 937 power modulo 2537 modulo n. And then, oh, excuse me, there's a typo here. 2282, that's not right. What did I do here? Oh, here in mathematical computation, I did it right. Just this mistake. Okay, I don't have to check anything. So this is done right. The answers are correct. It's just that I made a typo here. Sorry about that. Previously I had 2282, but no, it should be 2182, and it is 2182 here. Answers are correct. 1819 and 1415. And actually doing this kind of computation without calculator is crazy, of course. So I advise you to use computer algebra system like this. Maybe you'll be able to reduce those a little bit further using some exponent rules and congruence, but it's crazy. 2182 to 907's power modulo n 2537 turns out 1415, and previously 1819. So the conclusion is 1819, 1415. So 1819 SNT and 1415 ONP, we get the original message back. Okay, all right, and that's how you can handle this kind of encryption and decryption problem. As for the computation, this kind of computation looks like out of reach for any humans. But for computers, yeah, it's not too bad. Even when numbers are much bigger, it is still okay. But finding those P and Q back, that's gonna be out of reach even to computers. So that completes section 2. And I guess that's it for the entire course, including the appendix. Or maybe I will call it lesson 15, whatever it is gonna be.